Hello. This should be pretty easy. We're just going to examine some more of those proportionality relationships that we've been looking at in this chapter. The first one is very similar to what you've already seen. In fact, it'll follow pretty directly. What they're saying is, if we cut this triangle with a line parallel to this side here, we will break these two up into the same proportion. In other words, RU over US will be the same as RT over TQ. So let's label some of these links and see what we're talking about. Suppose we call that. And let's make this A, and this B, and this will be X, and this is Y. Now, the first thing we can spot real quick is that this small triangle, which was created when we drew the parallel line here, is similar to the large triangle, the one that was in a sense created from. Why is that? Well, we can use our angle theorem for this really easy. This angle is congruent to itself. It's shared by both triangles. So we've automatically got one angle that's congruent. All we have to do is find one more and we're done. Well, these are parallel lines. Here's a transversal. These are corresponding angles here. And we know that corresponding angles are congruent. So there's our other pair of congruent angles. And we have two similar triangles, the small one and the large one. So what do we know? Well, the corresponding parts are in the same ratios. So what are the corresponding parts? Now in this case, it's this TB corresponds to BQ, and RU corresponds to RS. And since they're similar, they have the same ratio. So we could have written A over A plus B, but that'll be harder. We'll just start with A plus B. That's the long side over the short side. And that has to be the same as X plus Y over the short side here, which is X. Now we can do something we did before when we wanted to show that we could add the denominator to the numerator on each side and still have a true proportion. What did we do? Well, I think we added 1 to each side, didn't we? Well, in this case, I think we can subtract 1 from each side and see what happens. For instance, over here, let's subtract A over A. From this. I guess I can just write it out over here. Minus that. And that equals X plus Y over X minus, how about X over X? That's also equal to 1, right? Well, when we do this, we've got common denominators here. All we have to do is subtract our A from the top and we get B over A. Over here, we perform our subtraction and get Y over X. Well, wait a minute. B is QT. A is RT. So, we just showed that B over A equals Y over X. And if you want to switch this, that's fine, because we know from our previous theorem that this implies that the two inverses are also equal. So we can write a over b equals x over y, which is the way they wrote it. RT is a, TQ is b. We got RT over TQ. Same thing here. RU is x, y is US, and here we have x over y. So, it's very easy from the fact of similarity of these two triangles to show that these proportions hold. The ratio of this to this and the ratio of this to this are the same. And this second one just tells us that if we have this case, where these have been broken up proportionally, then the line we used to make the cut, that must be parallel to this one. So now it goes both ways. If we find this to be true, then we know that these two lines are parallel. On the other hand, if we know these lines are parallel, then this is true. Now we have another theorem here that's really just an extension of our triangle proportionality theorem. It follows pretty easily from that. Number one, we're assuming these two lines are not parallel. If they are, it's really easy to show that things are broken up proportionally. But they're not parallel, which means that sooner or later they intersect. And we could just draw a line here parallel to these two to produce a triangle. Now we know from our triangle inequality that this section here, LY, I should say the ratio of this section to YU is the same as the ratio of this section, Z, that's an M right there, I drew over it, sorry, ZM over MZ. We got LY, pardon me, ZM over ZV, and LY over YU. On the other hand, we've got this one here, UW over WL is the same as VX over XM. And you can just keep combining these until you convince yourself that this is true. The transversals are always going to be broken up proportionally. I drew an extra parallel line here and was talking about YL when I probably shouldn't have. We can treat this one. Suppose I hadn't filled that in. Okay, let's do this the smart way and forget that I drew a line in there, because there's really no reason for that. Let this be the third line of our triangle. Or, pardon me, the third side of our triangle. Well, now we've just got the triangle the triangle proportionality theorem. We treat this as the side to which these two lines are parallel. And we've got something very similar. For instance, if we drew this point out here as, let's call it A, then we could right off the bat, when we cut this line, say that UY is the same as UA. Pardon me, the ratio of UY to UA is the same as the ratio of VZ to VA. And we could do that with this here also. It's adding extra lines in here. We're still cutting things up proportionally. There was nothing magical previously about the fact that we had one parallel line. We can draw as many parallel lines as we want and create as many proportionalities or proportions as we choose. Every time we do that, we'll create a ratio, and we'll create a ratio that is equal on each side. It's actually took me longer to explain it than it's probably worth. I think given the previous triangle proportionality theorem, it's very easy to see the truth of this one. This one here is a little less obvious, well, to me anyway. I drew a little picture that might help you see the sense of this. It's definitely not a proof. It's just a way of looking at it that might help you see what it is they're trying to say here. And what they're saying is that the opposite side is divided up in the same proportion as these two sides. In other words, the segment AD, or the length of AD, over dB is going to be the same as the ratio of this segment CA over CB. As this side gets longer, this section gets bigger. Why would that be? Well, if we're going to keep these two the same, I redrew it out here. This side and this side are the same length. Obviously, the only way we can extend this side, make it any longer than it is, without changing the shape of this, is to pull this in a little bit. In other words, everything else being equal, if all we do is extend the length of this side, we have to reduce the size of this angle. We also have to change this angle here. This side and this side should be the same length. We just swung this out here so that this side could intersect it. Well, when we did that, when we lengthened this side, you can see where this red part here intersects. I mean, this section is broken up at the intersection point. This right here is the angle bisector of the original reddish triangle. Reddish brown, whatever that is. See that this side is probably a little bit smaller than this side. In other words, the ratio of this side to this side is probably less than 1, because the numerator is a little bit smaller than the denominator. However, if I extend this side way out like that, rotate this, don't change the length of it, I've reduced the size of this angle. My angle bisector has moved over a little bit to here. And when this thing swung out like that, well, because of the angle, now this piece here is larger than this piece. So the way I've broken it up now, this section, which corresponds to this right here, is over the length of this section, over the length of this section, is going to be greater than 1. Previously, this was broken up into 2 segments. This would have been the shorter segment. And this is the shorter side. Now this is the longer side, and this is the longer segment. It's not a proof, but with any luck, it visually gives you an idea of what's going on here, what they're trying to tell you. Well, here we have a multiple choice. Figure out which one tain't necessarily so. Well, let's take a look. Remember our theorem. We have these 2 transversals cut by 3 parallel lines. So we know that they cut them up into the same proportions. So that PQ over QR equals UT over TS. And it's also true that PQ over PR equals UT over US. In other words, the small one over the big one is equal to the small one over the big one here, or either one over the whole thing. Either one over the whole thing. Those two ratios are also equal. This part over the whole, well, we got that from creating our similar triangles. And going back and forth between the sections, PQ over QR or PQ over PR, we just went back and forth by adding or subtracting 1. We've done that a couple of times. So let's see what we got here. PQ over QR. That's just what I was talking about. This section over the length of this section over the length of this section equals the length of this section over the length of this section. That's true. We just looked at a theorem which says exactly that. What about TS and UT? Well, that's just another way of writing pretty much the same thing. TS, UT. Those two segments, yes, it's a ratio of that, and then QR over PQ. So the ratio of this to this is the same as the ratio of this to this. That's true. So that works. What about QR over RS? Well, we got QR here and RS here. I don't think we have any theorems that say too much about this ratio. We could maybe say this ratio to this. That might mean something, but no. This segment to this segment, that ratio, don't think we have any theorems which address that particular ratio. And TS and RS. Yeah, we don't have a theorem that addresses the equality or inequality of those two ratios. At least I can't think of one. What about this one? Let's just make sure. I think this is going to turn out to be the one that's not true. Let's check it out. PQ over PR. Well, there's the one section over the entire side. And we know this is true from the similarity. And then, well, pardon me, we got to get to the second part first. We're getting PQ over PR, and that should be, that in fact it definitely is the same as UT over US. Is that what we have written here? Yes, it is. So it definitely has to be C. This is the one we can't say for sure is true. Can't say for sure that it isn't true either. We don't have any postulates or theorems that would tell us about this one way or the other. This, I'm referring to C here, QR over RS, and then TS over RS. Seems unlikely they would turn out to be the same, because it seems unlikely that QR and TS are congruent. In fact, I think you could probably show from the fact that they're not parallel that this is definitely, this is almost perpendicular to our parallel lines, whereas this is at an angle. Remember, the perpendicular distance is the shorter one, so the distance from here to here must be longer than this line here. So this definitely not only is not necessarily true, I think you can see that, at least from the look of it, it is absolutely untrue. And there's another one of those. Someone made a mistake. And I'm still voting for postal clerks as people most likely to make mistakes. You know, a few days ago I checked my box, and aside from all the usual junk mail that's not really addressed to anybody, I had 3 letters with actual names and addresses on them. One of them had my name and address. The other 2 had completely different names and different addresses. However, they did end in the same number. My address ends at a 4, and the other 2 also ended in 4. So I think the post office has a new type of mathematics where anything that ends in 4 is equal to anything else that ends in 4. I can't wait to see the bridges they build. Well, let's check this one out. Looks like he's starting out okay. Remember, this is a bisector. We know that because they put the little hash mark in here to tell you that each of these angles are equal, which means congruent, if you prefer. So this is a bisector, and we just showed that a bisector, well, we didn't really prove it, but we have the theorem, we just looked at it, that the angle bisector breaks up the opposite side into segments with exactly the same proportion as the 2 other sides. In other words, 10 over 16 should equal AD over 20, or totally generally, AB over BC should equal AD over DC. AB over BC. So, well, it's got this part right. This looks fine to me. AB over BC is 10 over 16. 20 minus x. Well, I'm not sure where that would have come from. I don't know. If we had the whole thing AC and called that x, then AD would be 20 minus x. Even that wouldn't be right, because AC would be x minus 20. That would make, this part would be x minus 20. Where the whole thing right here would be x. AC is x, and x minus 20 would be AD. But that's completely unnecessary here. We actually can just put an x up here, and then everything's good. As we have, then we'll have 16x. See if our answer makes sense. They didn't actually ask you for an answer, but what the heck? We're not busy, right? Well, and this reduces to, and with a little bit of computation, we end up with x equals 12.5, which actually makes sense. 12.5 over 20, actually I checked it with the calculator, and 12.5 over 20 is exactly the same as 10 over 16. That's the only small mistake he made. Which means I was probably wrong about this being a postal clerk. This is a pretty small mistake. I don't think it's a big enough mistake for a postal employee to make. It's too small. Maybe it really was a student. Well, here's one that's interesting. We've got 3 parallel lines and transversals. These happen to meet here, intersect, and form a triangle. But the same theorem still applies. They're broken up into equal ratios. And the thing about this is, I'm not sure we really need all of these. I think if we have any two, for instance, the ratio of this section to this section here should be the same as the ratio of this section to this section. That's also true for this section, but I'm just noticing that we've got a 2x and a 6x and a 6 and an 18. The whole thing looks less messy. But let's see if we can find x just using these two. Maybe not. But I like the idea of starting out with what's easy and go from there. So we got 2x over 6x equals 6 over 18. This is 1/3. X over x. So that's no good. Well, shucks. That won't actually get us anywhere. So the biggest problem with what I set up was the fact that by putting 2x over 6x, the x's cancel. And I don't have any way of solving for x. However, it's also true that I can say that the ratio of, say, this small one to the whole thing is the same as the ratio of this small one to the whole thing, or this large one to the whole thing. It's hard to say which one will work out better, but let's try putting, say, the ratio of this to this. That's another ratio that works, because this parallel line here and this parallel line, if we were to ignore this whole section here would be 2x plus 1 plus 2x. So we can't just cancel the x's. That's probably true if I come up with any equation that includes the 2x plus 1. So maybe I just messed up by picking these two sections, and I should have picked these two. Let's see what happens. How about 2x plus 1 over 2x equals 7.5 over 6. This might get us somewhere. Let's check. We can cross multiply. This here, that's 15x. 2 times 7.5. And that's 12x plus 6. Subtract x from each side. Pardon me. Subtract 12x from each side. And get that 3x equals 6, or x equals 2. And that's over here. At least that's a step in the right direction. The answer we came up with was one of the options. So, when setting this up, I tried to make it easy and outsmarted myself by losing the x's and ending up with an equation that basically said 1/3 equals 1/3. That's true, but it doesn't get us anywhere. We put something like this up in the denominator, then we can't cancel off the x's. Now we've got an equation that doesn't just fall apart as soon as we try to write it. And we actually have a solution for x that works. And it does work. We put, that'll be 4. This would be 5, and this would be 12. Now you check those, and they actually work. Such as, for instance, 4 to 12 is the same as 6 over 18. They're both 1/3. And it'll work for all of these. Now here's one that looks worse than it is. At least I hope so. They've got a whole bunch of unknowns here. Nearly half the alphabet they want us to find. Looks like this problem is going to be about the length of a Russian novel. But maybe not. It might be easier than we think. Let's check it out. Let's start down here at the right. What the heck? Just work our way to the left. What about F? Well, here we have transversals cutting two parallel lines, so the ratio of this section to this section must be the same as the ratio of this section to this section. Or another way of writing that is that f over 12 equals 10 over 15. And with a little bit of rearranging here, I mean, this is obviously equal to 2/3. Multiply through and we get 24 divided by 3, or f equals 8. Might as well put that in. Okay. What about E? Well, again, we have transversals, parallel lines cutting them, so the ratio of E to 12 is the same as the ratio of 5 to 15. So, let's separate this. We have 5 over 15 equals E over 12, or 15E equals 5 times 12, which is 60, but 4 times 15 is 60, so E equals 4. Well, so far this isn't too bad. Now we've got all the lengths on this side. Which may come in handy later. We'll see. What about D here? Well, if we just go from this point to here, this outline is a triangle, and this triangle here is cut by this line parallel to this side. And what do we know about that? Well, we know that the ratio of the length of this line to this line is the same as the ratio of this section to the whole thing, which is the same as saying that 10 over 25 is equal to d over 12.5. And I should separate this off so not get these things confused here. Here's E, here's F. Now we're finding D. Well, 10 times 12.5, that's 125. So we have that 125 equals 25D, or D equals 5. 5 times 25 is 125. So we can put that in here. What else don't we know? Well, what about B? We could find these. Problem is we don't have this one or this one. We could check the ratio of this to this, I guess. Yeah, that's not a bad idea. Why don't we do that? What would the ratio of this to this be? Well, I think it would be the same as the ratio of this little piece to the whole piece, or this little piece to this whole piece. Well, this piece looks easier to add up. There's absolutely no other reason to use it other than the fact that 20 and 10 is 30. And it's easy to spot. So a 30 goes in the bottom here. And there's a 5, so okay. And of course, 5 is not okay. We need to use this part here as our length. So it should be 25 over 30. That's the ratio of this side over the whole thing. Should be the same as the ratio of this over this. Which kind of makes sense. The closer this gets to this side here, the longer this part gets. And the closer this fraction gets to 1. Which makes sense, because if you move this far enough, it's going to be right on top. It'll be the same segment, and the ratio will be 1. So there's a certain sense to this. And that equals C over, pardon me, that equals 12.5 over C. And that should give us, so if we set this up, 25 over 30 equals 12.5 over C. We end up with 25C equals 12.5 times 30. We cross multiply. That's 25C equals 375, or C equals 15. And we can put that in here. Now what we need is A and B. Well, B should be pretty easy. Remember, these sides are broken up the same as these two sides. So 4 over 12.5 should be the same as 5 over B. And now what we need is a little bit of room, don't we? There we go. Hope I didn't make you seasick. 4 over 12.5. Let's section this off here. Or how about 4 over 12.5 equals 5 over B. So we have the 5b. Well, after we set this up, we'll get that 5b equals 4 times 12.5. That's 62.5. And when we divide that by 5, we get 15.625. So what's left? Well, all we have left here is A. And remember, we can pick any one of these now. For instance, the ratio of D over A is the same as 10 over the whole thing. Or 8 over this whole thing. Whichever one we like better. We could use any one of these to find A. So let's draw a little line off here and make sure we don't get our equations confused. And we'll take the whole thing. What the heck? Let's use this side just for fun. Okay, I blocked this off so we don't get confused. This is where we found D. And now we're working on our very last variable, A. And we can say that 10 over this entire length is the same as 5 over A. Well, what is this entire length? Well, we already figured this part out. This was 30. Plus 15.625 would be 45.625. 10 over that is the same as 5 over A. Well, that means that 10A equals 5 times 45.625. So when we multiply this out, we cross multiply here and get 10A equals 228.125. Well, but to get A we have to divide by 10. Hope you can see this on the bottom of the screen. Well, when you divide something by 10, all you have to do is move the decimal point over to the left one, so it's 22.8 and all this stuff, which I would just round off to 22.8. So we can put that up here. And now I think we have found every single measurement. We found F, E, D, C, B, and A. There's nothing here we don't know. Well, that's about it.